Today's problem was submitted by a viewer, and it says, compute the integral from 0 to pi over 2 of the cube root of tan x divided by sine x plus cos x squared dx. Okay, so let's write this out. So we have tan x, I'll just call it to the power of 1 over 3, divided by sine x plus cosine x squared. Ooh. That's really weird. I don't really know what... One thing crossing my mind is, can we even hope to find an antiderivative of this? We're looking for a definite integral, right? So maybe there is something... Maybe there's something we can do where we just figure out the value of this definite integral without actually finding an antiderivative. If we do have to find an antiderivative, what substitutions could we think of? The cube root is something that's really a little bit bizarre. Maybe some crazy substitutions are in order, like if we let u be equal to cosine x. Maybe we do some sort of phase shift thing, like sine plus cos is itself also a sinusoid. But it's shifted. So it's not really, that might not help because it doesn't really then, you know, sine x plus cosine x, this will be equal to a sine x plus phi for some values of a and phi. I believe a is probably root 2 and phi is probably pi over 4. So the problem then is that we don't really have the same argument to all of our trigonometric functions. Okay, so there's two things that are a little bit bizarre here. The first is the cube root on tan x. And the second is that this whole thing is being squared. Okay, what if I expand the denominator? So I have this. And I get tan x to the 1 over 3 divided by sine squared plus cos squared is 1. So this is 1 plus 2 sine x cosine x. there's an identity for this, right? This is equal to that's equal to something. 2 sine x cos x. I believe that's equal to sine of 2x, if my trig identities are correct. But then again, we still run into the problem that we want to I probably want to keep the argument to each of my trig functions that appear the same. But maybe now I can factor something in some way. I don't think anything about, any symmetries or anything like that are going to be useful. I mean, it looks like everything is positive between 0 and pi over 2. Okay, I might have made some progress here. So if I just make the substitution u is equal to tan x, just go through the standard substitution method, the integral, of course, becomes this. All I've done there is replaced tan x with u. Then if I replace the differential with that there, I know that this here, that's u squared. At the same time, I'm also going to factor a cosine x out of this thing in the bottom. So I end up with the sine becomes sine divided by cos, which is tan, and the cosine comes out, becomes squared. And cosine squared is 1 over secant squared, which is 1 over 1 plus tan squared, which is itself, again, that's 1 plus u squared, like that. So it cancels. So now I'm left with the integral from 0 to infinity of u to the 1 over 3 divided by 1 plus u squared du, which looks a lot simpler, but I'm still not sure if this is going to be terribly easy. Maybe I can what happens if I factor u out of the denominator? So now canceling some exponents, I have u to the power of negative 2 over 3. I don't know if this helps in any way. Wait. This exponent is supposed to be on the outside. Yeah, I've screwed something up. Hold on. Let me make sure I did this correctly. 1 plus u squared, and that's 1 plus u all squared. Yeah, the 1 plus u all squared is what remains. So let's write this out again. 0 to infinity, u over 1 plus u quantity squared. So I could factor out square root of u. Is this going to help at all? I don't see how this is going to work. The exponents just don't really seem to be cooperating. I'm not sure if this is if this integral is even easier than the one we had previously. I mean, the only thing I can say here is it looks like the integral is finite. You know, for very large values of u, this whole thing is roughly u to the power of negative 5 over 3, which has a finite integral. I mean, if I do something like, if I say v is equal to u to the 1 over 3, then dv is 1 over 3 u negative 2 over 3 du. And so u dv, let's say 3u dv, is equal to u to the 1 over 3 du. And this is 3v cubed dv is equal to u 1 over 3 du. And the denominator is 1 plus v to the 6, no, 1 plus v cubed squared. Now I have an integral from 0 to infinity. So the numerator, 3 v cubed dv divided by 1 plus v cubed squared. Is this any easier? What if I say this is, okay, let's look at v cubed over 1 plus v cubed squared. I'm going to call this a over 1 plus v cubed plus, I'm sort of piecing together some kind of strange partial fractions thing here, but I don't remember exactly how this is supposed to go. B plus c v cubed over 1 plus v cubed squared? Or is the v cubed term supposed to be on the left? Let's just see what happens when I do this. So this is a plus av cubed over 1 plus v cubed squared plus b plus c v cubed over 1 plus v cubed squared. So I need a to equal negative b. And I need a plus c to equal 1. So how about so 1 over 1 plus v cubed minus 1 over 1 plus v cubed squared. That's equal to 1 plus v cubed. Yeah, this is equal to my integrand. Okay, so my entire integral is now 0 to infinity. I'll pull the 3 out inside. I have 1 over 1 plus v cubed minus 1 over 1 plus v cubed squared dv. Is this any easier? What is the integral of 1 over 1 plus v cubed? That doesn't sound like anything I've ever seen. You know, again, I don't even know if this substitution here is the best way to solve this problem. You know, at this point, I don't really want to go all the way back to the original question and try a different path. I could just try a different trig function, you know, u is equal to sine x or u is equal to cos x, and see what happens. Maybe I'll give one of these a shot. The cube root, though, is still really gonna throw things off. I mean, this looks like it should be an integral that's doable. But I don't know an integral of 1 over 1 plus v cubed or 1 over 1 plus v cubed squared. Wait, what about and even if I just if I just do something naive, like think of a logarithm, log of 1 plus v cubed squared. You know, the derivative of this is 1 over 1 plus v cubed squared times 2 1 plus v cubed times 3v squared. So we don't have the right, we don't even have the right power of v in the numerator. Does this do it? This looks, yeah, why did I not think of this earlier? Why is it, why? Okay, let me just make sure here. So integral 3v cubed dv over blah blah blah. So I'm letting w equal that denominator. W is equal to 1 plus v cubed. Oh. So dv. No, that's not. Hold on. 3w squared dw is equal to 3v squared dv. Yeah, that's this probably won't work. Yeah, I don't know. This appears to be the most simplified version of the integral that I can get to. This looks like it should be something very easy to integrate. I don't know if there's a standard antiderivative for 1 over 1 plus v cubed. So, I mean, I think I don't want to just keep a video going where I'm not really making any progress. So I might have to just cut this one here and say that I'm stumped on this. Like I said, I don't even know if this is the right or the most straightforward direction doing this substitution. Maybe there's some sort of trig substitution or trig identity you can use to make things simpler here. The 1 over 3 really makes things a little weird. Like, is there a triple angle formula or something like that that becomes important? I don't know. But I think I'm going to have to leave it here. If I have any thoughts about this one, things that I think might actually be useful to pursue, then maybe I can come back and add to this or leave a comment in the description. But yeah, if anyone has any ideas for what you might do next or the direction you might go at the very beginning, leave a comment down below. Thanks for watching. So I've had a little bit more time to think about how to compute this integral ever since I started going through the computations the first time. And even though I got stuck at some point when I previously went through some attempts, I had a very brief exchange with the person who submitted this problem to me. And one thing they said sparked an idea that, to be honest, I probably should have pursued when I went through the integral the first time. So what I'm going to do is pick up from where I left off on my solution so far and continue with that idea. But before I do that, I wanted to start from scratch and go through the same set of computations again until the point I got stuck, just to make sure that I was in fact doing things correctly. I don't want to pick up from a place I left off and find out later that what I'd gotten to was the result of some error. So I'm going to go through the same set of computations, and then when I get to the point I was at before, I'll explain what the next step that I'm going to pursue is. Okay, so this is as far as I'd gotten before. It's an integral which looks much more simplified than the original one, although still not the easiest thing to compute. You know, I don't know what an antiderivative of that is. Not sure what an antiderivative of that is. But what I should have done at this point is realize that this denominator, 1 plus v cubed, that can be factored. And so I could potentially use partial fractions on this term. This term is, of course, the same as this one squared. So use partial fractions on this. I should be able to figure out very quickly a partial fractions decomposition on this. And hopefully we get to something which is in a form that we can integrate more easily. So we note that 1 plus v cubed is equal to 1 plus v times 1 minus v plus v squared. I think. Let's just make sure this is correct. So we have 1 plus v squared. Wait, 1 minus v plus v squared plus v minus v squared plus v cubed. Yeah. So if we say 1 over 1 plus v cubed is equal to a over 1 plus v plus b plus cv over 1 minus v plus v squared. Let's see if we can deduce a, b, and c. Okay, so matching coefficients, we have a plus b is equal to 1. b minus a plus c is equal to 0, and a plus c is equal to 0. Okay, so a is equal to negative c. So we have b is equal to negative 2c. So c is negative 1/3, which means a is equal to 1/3. and b is equal to 2/3. So we should have 1 over 1 plus b cubed is equal to 1 over 3 times 1 over 1 plus v plus 2 minus v over 1 minus v plus v squared. Let's just verify now that when we expand this, that we do have equality here. So 2 minus 1 minus 1 plus 1 minus 1, 3, yeah, so this works. Okay, so this is correct. This is the correct partial fractions decomposition of 1 plus v cubed. I'm not really sure now, like whether anything here will be easier or harder to integrate. Like we can integrate that, of course, but this isn't the easiest thing to integrate. And I wonder if we should, you know, what we should have done is just do a partial fractions decomposition on this thing directly. I'm not really sure. Because now I have 1 over 1 plus v cubed squared is equal to 1 over 9 times 1 over 1 plus v plus 2 minus v over 1 minus v plus v squared squared. And you know, I'm going to end up with something which would require a further partial fractions decomposition. You know, I'll have that term squared, which is fine. I'll have that term squared, which would technically require yeah, if the cross term though will give us something that could be further decomposed. But how do we deal with the integral of something like this? I mean, this seems like it's going to be a nightmare to try and expand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 unknowns. No, maybe I'll just expand this and see what we get. 1 over 9 times 1 over 1 plus v squared plus 2 minus v squared over 1 minus v plus v squared squared plus 2 times 2 minus v over 1 plus v times 1 minus v plus v squared. Wait, does this thing have nice roots? This has roots, should I factor, maybe should I factor that thing as well? Does this have, is this the golden ratio thing, polynomial? No, it's not. So it doesn't have, yeah, this doesn't have any real roots, right? Yeah. Plus or minus the square root of b squared minus 4. Yeah, okay. Yeah, that's an irreducible polynomial. Okay. So 4 minus 2v over 1 plus v, 1 minus v plus v squared. I want this to be equal to, I won't use a, b, and c again. Let's go d over 1 plus v plus e plus fv over 1 minus v plus v squared. So let's rearrange first. D plus E plus E minus D plus F V plus D plus F V squared. Okay. So D plus E is equal to 4. D plus F is equal to 0, and E minus D plus F is equal to -2. So D is negative F, E minus F is equal to 4, E plus 2F is equal to -2. Let's go top minus bottom. So F is -2, D is equal to 2, and E is equal to 2. Okay, and let's check to make sure that this one also works properly. So I've got 4 minus 2v over that, which works. Okay, so this gives us 1 over 1 plus v cubed squared is equal to 1 over 9. One over 1 plus v squared. 2 minus v squared. Plus my new decomposition. Like that. Oh my goodness. So my integral that I want, this thing, is equal to 3 times the integral from 0 to infinity, 1 over v cubed is 1 over 1 plus v. So the numerators are 1 and 2 minus v. That's the first term, minus, I'm missing a factor of 3 there? Yeah, there's a 1 over 3 in front. Minus 1 over 9 times this junk, okay. We bring the 3 inside, at least that is gone. And we there's no cancellation of things here, not exactly. I don't see an easy way to do this. This is the only one that I can immediately identify an antiderivative for. Maybe we could do something, add and subtract something to the numerator here so that it becomes, we can use a substitution, but that means we still have an extra term. I would need to be able to integrate 1 over that. I don't know. I don't see it. Integrating 1 over 1 plus v squared. Don't know. I'm also a little bit, well, no, I guess like this integral here on those bounds is infinite, but then this one here, that one is also infinite and should cancel at like the appropriate rates. The rest are all finite. These integrals you can see are finite. I'm not sure. I mean, so the thing that the person who submitted this in our correspondence after my first attempt said that they had to look up integrals of rational functions. So I've clearly got this down to a bunch of rational functions. Even originally, my the expression that I have here, just a couple of rational functions. Maybe there is some expression for an antiderivative of both of these. I don't know what it is off the top of my head. Even what I had earlier is a lot more straightforward than the original thing with the trigonometric functions. At least it looks like it, but I don't know. You know, I'm stumped on how to come up with an actual antiderivative for this. And I mean, if I'm basically one step away from the correct answer, except that you just need to look up a table of integrals for these things, then, you know, okay, fine. I'm happy with being that far, I suppose. So I think I'm going to leave it here. I don't know. The next thing I would do here, if I absolutely had to find the answer to this thing, I would just look up how to integrate these general, fairly general rational functions, you know, linear divided by quadratic, something 1 over quadratic and quadratic over quartic. I just look those up and go ahead and plug things in. I don't know if there's like some slick way of deriving what these things, what these integrals are equal to, but yeah, I'm not going to spend, this video is already going to be quite long, so I think I'm just going to call it here. But if you have an approach, if you know exactly what the answer is or how to derive it, you know, let me know in a comment below. Thanks for watching.